Okay, so now we're on to chapter 10, which deals with, as you can see on the screen, the two concepts which are related to each other, bonding theory and the molecular structure. Now, the first thing we're going to talk about here is the whole idea of molecular geometry, which basically means the three-dimensional shape of a molecule, all right? And what you see on the screen here are three examples of molecules, all right? The first one is the oxygen molecule, which we all know is a diatomic molecule, right? Now, because it's diatomic, the shape of this molecule, the three-dimensional shape of this molecule will be linear, right? There's no other alternative. That's basically how things are. If you have two atoms in a molecule and they're bonded to each other, then this shape must be necessarily linear. So that is true not only for oxygen, but true for other diatomic molecules, such as hydrogen, nitrogen, oxygen, as I said before, and the halogens, chlorine, fluorine, bromine, and iodine. These are all diatomic molecules, and therefore their shapes would be said to be linear. Now, if you have three atoms in a molecule, such as in the case of carbon dioxide here, there are two possible arrangements in terms of the geometry. One would be what you see here for carbon dioxide, which is linear, and the other one would be for water here, which is bent, all right? So this begs the question, what determines the shape adopted by such a molecule? Why is it that carbon dioxide exists as a linear molecule while the water molecule here exists as a bent or V-shaped molecule, all right? Okay, so this brings us to the theory that is used to explain all this. It's called the valence shell electron pair repulsion theory, abbreviation VSEPR, or some people like to say the VESPER theory, all right? And basically, what this theory says is that the molecular geometry is based on the idea that pairs of electrons in the bonded atoms, and this is in particular reference to the central atoms, will repel one another. So at this juncture, we need to define what is called an electron group. An electron group is any collection of valence electrons that are localized in a region around a central atom that repels other atoms of the valence electrons, all right? Other groups of valence electrons. So basically what the theory is saying is that the shape that is finally adopted by any molecule is based on the repulsion between these electron groups, all right? And because of these mutual repulsions between these electron groups, then as I said before, this leads to the what we call the electron group geometry, which we're going to see shortly will lead to the actual shape of the molecule, the geometry of the molecule itself. All right. Okay. So basically, what you see here on the screen are the possibilities in terms of the electron groups arrangement. All right. Now there's one that is missing, and that is the two electron groups. Right. Now what we have here, I call these balloon models to represent how the electron groups. So each of these balloons represent an electron group and how they are arranged with respect to each other. If you have two electron groups, then the arrangement would be a linear arrangement, which is not shown here. So let me try to use my limited artistic skills to show you what that looks like. So if that is one balloon here and that is one balloon here, each representing an electron group, then if you can draw a straight line right through like this, um, then that's a linear arrangement. So this would be the linear arrangement for two electron groups, as stated here. For two electron groups, that's the geometry. For three electron groups, then the shape would be, or the geometry would be trigonal planar, which is represented by this arrangement right here. All right. In the case of four electron groups, the geometry will be tetrahedral, as you can see right here. And then in the case of five electron groups, the shape will be trigonal bipyramidal, as seen here. And then finally, if you have six electron groups, the shape will be octahedral, as represented by this model right here. All right, so those are the different possibilities. And there are more, but for our purposes, we'll just stop at the six electron groups octahedral geometry. All right. So it's very important that you understand this. And the key thing you need to remember is that, and I probably should have mentioned this before, the reason why these are the arrangements is because of the fact that these electron groups will repel each other to be as far apart from each other. So for example, in the case of the linear adoption, basically this would be the most stable arrangement so that these electron groups will be as far from each other as possible. And the same is true for the others, for the trigonal planar, for the tetrahedral, and so on and so forth. All right. Okay. So the next thing we're going to talk about is how do we represent the arrangement of electron pairs around the central atom. And we do that by using what is called the VSEPR notation, right? And basically, according to this notation, the letter A represents the central atom in the molecule. The atoms bonded to A will be represented by X, and the electron pairs on the central atom will be represented by E, all right? So for example, the designation for the water molecule, which is shown here, the VSEPR notation would be A, X2, E, all right? A would be the oxygen, X would be the hydrogens, and the E, oh, by the way, this should be 2, represents the electron pairs. There are 2 of them, all right? So that's basically how the VSEPR notation works. Let me use another example. Let's say in the case of carbon dioxide, for which the Lewis structure is this, right? In this case, carbon would be the central atom, so that would be the A atom, and the oxygens would be the X atom, and there are no lone pairs. So therefore, the VSEPR notation for carbon dioxide would simply be AX2, all right? So that's basically how we use the VSEPR notation, and that basically makes life easier for us to summarize and organize to determine the type of shapes that the molecules will adopt. Basically, if you have a group of molecules having a particular VSEPR notation, then they will all adopt the same molecular shape, all right? Okay, so let's summarize what's going on here with respect to different molecules, their VSEPR notation, and the type of shape that they will adopt. So the first type of molecule we're going to look at, excuse me, is a molecule that has 2 electron groups, right? The electron group geometry of that molecule will be linear, and there are no lone pairs here. And this would be the VSEPR notation. And the result would be that the molecular geometry would be linear, where the angle between the bonds would be 180 degrees. And one example of this, a good example of this would be beryllium chloride. And this here basically the molecular model representation of that molecule. All right, so that's basically all there is to it when it comes to molecules where you have only 2 electron groups around the central atom. All right, as we said before, the shape adopted is due to the fact that the electron pairs around the central atoms, or more specifically the electron groups around the central atom, will repel each other to be as far apart from each other as possible, all right? The geometry, the final geometry of the molecule is not determined by the lone pairs of electrons, right? So in other words, when you're looking at the shape of the molecule, in this case, there are no lone pairs on the central atom, so therefore that will not be affecting the shape of the molecule. Now, that will not be true for all molecules, of course, as we're going to see in future examples. So the next example we're going to look at is where we have 3 electron groups around the central atom. As we said before, the geometry adopted by those electron groups will be trigonal planar. There are 0 lone pairs of electrons, and of course the VSEPR notation would be AX3, and this would be the molecular geometry adopted by the molecule. And let me just say something which I should have said in the previous slide. Basically, if you have 3 electron groups and no lone pairs among those electron groups, then the electron group geometry and the molecular geometry is going to be the same, all right? And you're going to see that pattern repeated over and over again in the future examples I'm about to show you. The bond angles would be 120 degrees, all right? That would be the spacing between the bonds around the central atom. And an example of this would be boron trifluoride, for which this is the molecular model, all right? Now, the next example we're going to look at is where we have 3 electron groups, just as we have here, but one of those electron groups would be a lone pair of electrons, all right? Now, the electron group geometry will still be trigonal planar. The VSEPR notation will be AX2E. And if you look at the actual shape adopted by the molecule as defined by the atoms, you'll see that the shape is angular. And if you compare this to this, you'll notice that the difference between them would be that where you have an X here with a bond between it and the central atom, there is no atom here, and instead you have a lone pair instead of a bonding pair on the A atom right here. So therefore, as a result, the shape adopted by this molecule will be a bent or angular shape. Now, because the number of electron groups are the same, the bond angles would be the same approximately as well. And a good example of this would be the SO2 molecule. And this is the molecular model representation of that molecule. All right. So that's basically what happens where you have 3 electron groups where one of them will be a lone pair. All right. Okay, continuing our look at different types of molecules. Here we have a situation where you have 4 electron groups. As we said before, the electron group geometry would be tetrahedral, and in this case you have 0 lone pairs. So therefore, well, here the VSEPR notation would be AX4, and as we said before, if there are 0 lone pairs, then the electron group geometry and the actual molecular geometry will be the same, which is a tetrahedral arrangement, and the bond angle in that case, the spacing here in terms of the bond angle would be 109.5, and an example of this would be the methane molecule, and this is the molecular model, representation. All right. So this would be the shape adopted by molecules having this particular VSEPR notation. All right. Now, the next example we're going to look at is where you still have 4 electron groups, but one of them would be a lone pair. So this would be the VSEPR notation, and the shape adopted by this molecule would be the not tetrahedral, but trigonal pyramidal. All right. And if you compare this to the tetrahedral, you see that the difference between this and the tetrahedral is that where there's a bonding pair of electrons here connecting the A to the X, there's a lone pair here. All right. So therefore, the shape is established by the other atoms that are here. And therefore, the shape is, as I said before, trigonal pyramidal. And the bond angles is going to be 109.5 because of the tetrahedral arrangement of the electron groups. A good example of this would be ammonia, and this would be the molecular model representation of that compound. And then if we go from 4 electron groups, one of which is a lone pair, to 4 electron groups, 2 of which are lone pairs, this would be the VSEPR notation, and this would be basically the shape adopted by the molecule as defined by the atoms. And if you compare this to this, you'll see that basically to get from here to here, we remove the X here, you're left with a lone pair here. So therefore the shape will be adopted by what is left, which would be the bent or angular shape, and the bond angle here, because again of the tetrahedral arrangement of the electron group, the bond angle here will be 109.5. A good example of this would be the water molecule, and this would be the actual molecular model representation of the water molecule. And then we get to a situation where we have 5 electron groups, no lone pairs. The electron group geometry would be trigonal bipyramidal. This would be the VSEPR notation, and this would be the shape adopted by such a molecule. And as you can see, it's a more complex structure than the others that we have looked at. So there are different bond angles depending on your perspective. If you're looking at, for example, from this X, in fact, let me use my pen here. If you look at this X to this X, the bond angle here is 180 degrees. If you look from this X to this X, the bond angle will be 120 degrees. And if you look from this X to this X, the bond angle here would be 90 degrees. So it depends on which bonds you're looking at, the actual value of the bond angle. An example of this molecule would be phosphorus pentachloride, and this would be the molecular model representation for that compound. And then we get to different situations where you have 5 electron groups, but the number of electron pairs vary. So in this case here, we have one lone pair of electrons. So therefore, the VSEPR notation would be this, and this would be the shape adopted by the molecules. And again, we have different bond angles depending on your perspective. And this would be an example of a molecule that would adopt this shape. And this would be, of course, the molecular model representation. If you have two lone pairs for the same number of electron groups, then this would be the shape adopted by the molecule. It will be a T-shaped molecule. And here are the bond angles and an example of a molecule that will adopt that shape. And then if you get to where you have 5 electron groups, 3 of them are electron lone pairs of electrons. This would be the VSEPR notation. This would be the shape adopted by the molecule. And you'll see that as you go from here to here, all you have to do is remove this X, leaving behind a lone pair, and you end up with this. This shape will be linear, which means that the angle will be 180 degrees, which means that the Lewis structure, or the formula I should say would be, or an example I should say would be this right here, xenon difluoride, and this is the molecular model representation of that compound. Then we get to situations where you have 6 electron groups, and here we have no lone pairs of electrons. This is the VSEPR notation, and this would be the shape adopted by such a molecule, octahedral. And again, we have different bond angles. And the example that is shown here is sulfur hexafluoride, which adopts that shape, and this would be the molecular model representation. Then we get to this same number of electron groups where one of them is a lone pair. This would be the VSEPR notation, and this would be the shape adopted by the molecule. All right, so if you compare this to the previous one on the previous slide, you remember that there's an X here. So to get from that to this, we remove that X, leave behind a lone pair, and we end up with a square pyramidal shaped molecule. The bond angles are all going to be 90 degrees, and an example of this would be the bromine pentafluoride molecule, and this would be the molecular model representation. And then finally, again, where we have 6 electron groups, in this case, 2 of them would be lone pairs of electrons, and basically this would be the shape adopted by such a molecule. This would be the bond angle for this molecule. Again, an example is shown here of this representation, or the molecule that will adopt this shape, xenon tetrafluoride, and here would be the molecular model representation. So those are the examples, and those are the different shapes of molecules based on the number of lone pairs and number of lone pairs and electron groups around the central atom. Now, what I want to show you is a table. So let me go to here. And this table is a summary of what we just discussed. So you'll have that to refer to. Where shall I find that? Tables, okay. Okay, so this link here, which gives you the different geometries, it's basically the same thing as I described earlier, but it's summarized in one table, all right? There's one difference is that in that the letter E is used to represent the central atom as opposed to A, which is what we used in the slides that you saw earlier. But pretty much everything is the same. So you can use this to refer to when it comes to predicting the shapes of molecules. So usually problems that are given when it comes to this are problems where you're given a formula and you're asked to determine the shape of the molecule. So I'm just going to choose some arbitrary examples so that you see how this works. And you'll see why it's important for you to know what the Lewis structure is to begin with. So you need to determine the Lewis structure in order to determine ultimately what the shape of the molecule will be. So the first example I'm going to use here is, let me use phosphorus trichloride. Let's use that example. So we go through the steps as we did before to determine the Lewis structure. P, we look up the valence, the group number for phosphorus, which gives you the number of valence electrons, which is 5. And for chlorine, it's 7, but we have to multiply by 3 because we have 3 of them, so that's 21. And then we add these together to get 26 electrons, which is equal to 13 pairs, all right? So we put the phosphorus in the middle, surrounded with the chlorines, and then we put the bonding pairs 1, 2, 3, then 4, 5, 6, 7, 8, 9, 10, 11, 12, and then the 13th pair would go on the phosphorus. Of course, as usual, we need to calculate the formal charges. So in the case of phosphorus, the formal charge is 5 minus half of 6 minus 2, and that will give you 0. And we do the same thing for chlorine. That will be 7 minus half of 2 minus 6 gives you 0. So there are no charges on these atoms. So therefore, the question now is, what is the shape of this molecule? So, of course, as I said before, you can go to the table. And, well, firstly, let me go back to this here. So basically what you do is look at the central atom, and you'll notice, well, actually, all you have to do is look at or determine the VSEPR notation, right? And basically the VSEPR notation would be, in the case of this molecule, A would be for the phosphorus, X would be for the chlorines. There are 3 of them, and you have a lone pair on the central atom. So that's AX3E. So if you go to the table here and look up which shape would be adopted, AX3E, that would be this right here, EX3E. So the shape here would be trigonal pyramidal, all right, or trigonal pyramid. So therefore, the answer here for this one is that the shape is trigonal pyramid. All right, and that's how you do that. All right. Let me do another example. So let's see. I think this is the example I did in class, or one example I did in class. Okay, so we count up the valence electrons. Carbon would be 4, oxygen would be 6, chlorine would be 7 times 2, so that's 14. So when you add these all up, you're going to get 24 electrons, which is equal to 12 pairs, all right? Put the carbon in the middle, surround it with the chlorines and the oxygen. We put the bonding pairs, 1, 2, 3, then 4, 5, 6, 7, 8, 9, 10, 11, 12. Do the formal charge calculation for carbon, which is 4 minus half of 6 minus 0. So that's 4 minus 3, so that gives you plus 1. So there's a plus charge on the carbon here. We do the same thing for the chlorine. So for each chlorine, it's 7 minus half of 2 minus 6 equals to 0. So there are no charges on the chlorine. And then we do the same calculation for the oxygen. That would be 6 minus half of 2 minus 6 equal to minus 1. So the oxygen has a minus 1 charge. This pair of electron comes here to form a double bond. So you're going to end up with Cl, C, Cl, double bond O, and then this here, all right? So this would be the lowest structure. So what's the VSEPR notation? A for the carbon, and X3 for the 3 atoms bonded to the carbon, and there are no lone pairs. So we go to our table here again to figure out which, what's the shape? AX3, which would be this right here. So therefore the shape adopted by this molecule would be trigonal planar. So go back to this here. So the shape here would be trigonal planar. All right, so that's basically how that is done. All right. Okay. Let me see here. Okay, so that's basically it. So next class we'll be moving on to talking about polarity. All right. Okay.